Not all series converge. Let's suppose that a series converges. So let's suppose that the sum k goes from 1 to infinity of a sub k is equal to L. And formally, what that means is that the limit as n approaches infinity of the finite sum k goes from 1 to n of a sub k is equal to L. Right? To say that the infinite series equals L is to say that the limit of the partial sums is L. I can modify this slightly without affecting the limit L. What I mean is that the limit as n approaches infinity of the sum k goes from 1 to n minus 1 of a sub k is also equal to L. Why is that? Both of these amount to adding up a bunch of terms in the sequence and seeing what I get close to. Let me be a little bit more precise to see formally why I can conclude that these two limits are both equal to L. I mean, assuming the series converges to L. Let's see. So I can define the nth partial sum as the sum k goes from 1 to n of a sub k. And to say that the series k goes from 1 to infinity of a sub k has value L is just to say that the limit of the nth partial sum as n goes to infinity is equal to L. Right? This is the definition of this. Now here's the subtle point. The limit of s sub n equals L as n approaches infinity is the same as saying that the limit of s sub n minus 1 as n approaches infinity is equal to L. Why is this the same as this? Well, this is saying that if I choose little n big enough, I can get s sub n as close as I like to L. Well, this is really saying the same thing, right? If I choose n just a little bit bigger, 1 bigger, then I can guarantee that s sub n minus 1 is just as close to L. So asserting this limit is really the same as asserting this limit. But this statement can be rewritten using this. So what this last statement is really saying is that the limit as n approaches infinity of, and now what's s sub n minus 1? Well, I'll use this up here. That's saying the sum k goes from 1 to n minus 1 of a sub k is equal to L. So I've got two sequences, both of whose limits are L. And that means the limit of their difference is 0. Okay, so I've got these two sequences, and they've both got a common limit of L. So I'm going to take their difference. Let's see what I get. So if I take their difference, I get the limit as n goes to infinity of the sum k goes from 1 to n of a sub k minus the limit n goes to infinity of the sum k goes from 1 to n minus 1 of a sub k. And that's L minus L, so this difference is 0. But now I can simplify this a bit. All right, this is a difference of limits, which is the limit of the difference. So this is the limit as n goes to infinity of the difference of these two things, which is the sum k goes from 1 to n a sub k minus the sum k goes from 1 to n minus 1 of a sub k. But now what's this? Well, this is really the limit as n goes to infinity of this sum is a sub 1 plus a sub 2 plus dot 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 plus a sub n minus, what am I subtracting here? I'm subtracting a sub 1 plus a sub 2 plus dot 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 plus a sub n minus 1. So if I add up a sub 1 through a sub n and then I subtract everything except for a sub n, what I'm really taking the limit of is just a sub n. So this is the limit as n goes to infinity of just a sub n by itself. And what we've said here is that that limit is 0. So the limit of the nth term is 0. So what have we proved? So the conclusion was that the limit of the nth term is 0. But the assumption at the beginning was that the series converged to L. So what we've really shown is the following. We've shown that if this series converges, then the limit of the nth term is 0. So let's turn that around. Let's take the contrapositive. So here's the original statement. If the series converges, then the limit of the nth term is 0. And here's the contrapositive. I just turn it around. If the limit is not 0, meaning that either the limit doesn't exist or the limit does exist but is some number that isn't 0, then the series has to diverge. Because if the series did converge, then the limit would have to be 0. What we have here is a test for divergence. Well, here's how this works. This is the question that we're always being asked. Question: does the series converge or diverge? And what we can do now is we can take a look at the limit of the nth term. And if that limit is not 0, then I know that the series diverges. On the other hand, it's important to keep track of the direction that this argument works in, right? If it happens that the limit is equal to 0, then the series might converge, it might diverge. In that case, this test is silent. It doesn't tell us any information. But if we know that the limit is not 0, then I know that the series diverges. Let's try this on an example. So the original question was this: does the series n goes from 1 to infinity of n over n plus 1 converge or diverge? We'll look at the limit of the nth term. So let's look at the limit as n goes to infinity of the nth term, which is n over n plus 1. That limit is 1, and 1 is not 0. So the series n over n plus 1, n goes from 1 to infinity, diverges. And that hopefully makes sense. Because to say that the limit of n over n plus 1 is equal to 1 means that this series involves adding up numbers that eventually are very close to 1. And if you add up a bunch of numbers that are very close to 1, well, then you're almost adding up 1 plus 1 plus 1 plus 1, and that certainly diverges. In this case, because the limit isn't 0, right, it can't be that the series converges. Because if the series were to converge, then this limit would have to be 0. But the limit's not 0, so the series must diverge. There's a lot of stuff going on here. So if you're having some trouble keeping track of all the moving pieces, here's a different way to think about what's going on. Think way back to the beginning of this talk. The very first thing we were looking at was this. If a series converges, then the limit of the nth term is equal to 0. Now, starting from that premise, we then concluded this, that if the limit of the nth term is not 0, then the series diverges. But putting these two statements next to each other, it can be a little bit confusing, right? Why is diverges the conclusion of this statement, but converges is the assumption that I have to make over here? Maybe they look like they're out of order. Well, one way to think about this is to make it a bit more real world. Instead of thinking about series, let's think about rain and clouds. If it's a rainy day, it's then a cloudy day, right? The rain has to come from somewhere. So raining implies cloudy. What happens if I negate these, right? What happens if it's not raining? Is it then necessarily not cloudy? No, that's not true. There's plenty of days when there's no rain, but there's still clouds in the sky. What if I turn this implication arrow around, right? Is this a true statement? Yes. If it's not cloudy, then it's not raining. Because if it were raining, it'd have to be cloudy. So it's that same kind of thinking now that I want to apply to this statement about series. I'm starting with the statement that converges implies the limit of the nth term is 0, right? I'm starting with a statement like rain implies clouds. And now I want to turn it around. So I want to say not converges and not the limit of the nth term is 0, but that means I have to also reverse the implication arrow. This is called the contrapositive. So what is this statement saying? It's saying that if it's not the case that the limit of the nth term is 0, which I could write this way, then the series doesn't converge, which is just another way to say it diverges. And that's the statement that I ended with, right? I'm ending with the statement that if the limit of the nth term isn't 0, then the series diverges. But it's super important to keep track of the direction of this relationship. This statement, diverges implies the limit of the nth term isn't 0, that statement's not true, right? Just like not rainy implies not cloudy isn't a true statement. But this statement is true. If the limit of the nth term isn't 0, then the series diverges.